Okay, so once again, good evening. So last time we were going to discuss about asymptotic analysis, which is the mathematical technique used to analyze the behavior of functions as the input size grows towards infinity. So it involves studying without necessarily looking at the exact values of the function for input.
Pamute po.
Okay, so in IT, no, asymptotic analysis is commonly used to analyze the performance of algorithm, as what we discussed last time. So by characterizing how their running time or space requirements grow as the input size increases, no, this is typically done by expressing the running time or space complexity of an algorithm as a function of the input size, and then analyzing the growth rate of these functions as the input size gets very large. As what we discussed last meeting, that asymptotic analysis is often expressed using big O notation, which provides an upper bound on the growth rate of functions. Let's say, for example, if the running time of an algorithm is big notation n multiplied by 2, it means that the running time grows no faster than n greater than 2 up to the constant factor as the input size is increases. Okay, I'll just want to give you a video presentation, of course. This will be a guidelines, no, for asymptotic analysis, no, because I think even in programming, no, we need to accept the fact that we need to understand what will be the possible guidelines for us to have asymptotic analysis. Okay. Again, I forgot, if you have some additional inputs, do not hesitate to push your inputs or additional ideas in our chat box, so we could able to, of course, to address, no, or if you have some concerns later.
Ready for connection.
This is our task. We need to evaluate how much this statement has been executed. This is the way we are calculating the time complexity, right? We know that loop executes n times. So is the statement. Statement also executes n times because this statement is within this for loop. As this loop runs from 1 to n, this statement also executes n times. So it is clear that total time will be big O of n. Obviously, I am assuming that this statement is taking a constant amount of time. Then definitely the total time will be big O of n, right? Here n means the growth is linear. Now let's see the second guideline. The guideline related to nested loops. Here is the one. We have two for loops, right? And we don't have them separately. We have this in the nested form, which means that one loop is within another loop. Here you can clearly see we have an outer loop, then within that we have another loop. This loop, which is the outer loop, runs from 1 to n, and the inner loop also runs from 1 to n. And within this inner loop you have a statement. You need to evaluate how many times this statement has been executed. Outer loop executes n times and inner loop also executes n times. Apart from this, we also know that for I is equal to 1, the inner loop runs from 1 to n. For I is equal to 2, inner loop again runs from 1 to n. For I equals to 3, inner loop again runs from 1 to n, and so on. So from this idea, it is clear that total time will be n into n, that is order of n square. So the growth is quadratic in this case. So nested loops can be handled in this way. This is how you're getting a quadratic growth, because this is n into n, right? For each value of I, this will execute n times. So that is why it is n into n, and this gives order of n square. Now the third guideline, the consecutive statements. We have these consecutive statements one by one. You can see that we have these statements like I have declared an integer variable x and I have assigned a value 2 to it. Then I have declared an integer variable I. Then what I'm doing here is I'm incrementing the value of x. Obviously the total time in this case will be 3 units because each statement executes one time and there is no loop in this case. Then definitely total time will be 3 units. Now talking about this loop, obviously this loop executes n times, no doubt about this. We will calculate the time separately, okay? After that, we have this nested loop, which obviously runs n square times. Then the total time will be n square units, right? Now, what you have to do in the case of consecutive statements is that you should add all these times, right? Then it will give us the total time. This will be n square plus n plus 3, isn't that so? Then obviously, this will be big O of n square or order of n square. The time complexity of this particular code is order of n square. Why is that so? We already know how to calculate the time complexity. We have fn is equals to n square plus n plus 3. This is the function under consideration, right? Let's take gn equals to n square. I'm assuming this will be the upper bound. Now the question again is fn equals to big O of gn? If that is the case, then definitely order of n square will be the time complexity. We'll compare fn and gn. We'll choose some value of c. Let's take c equals to 2 because in this case, this is just n square. I am just taking one higher value than this. This is 1 into n square. I will take it 2 into n square here. Then the inequality becomes n square plus n plus 3 is less than or equal to 2 into n square, right? Now we can solve this for n. This will become n square minus n greater than or equal to 3. We can take n common from here. Then it becomes n into n minus 1 greater than or equal to 3. Finally, we will get these two inequalities, n greater than or equal to 3 or n greater than or equal to 4. So it is clear from this fact that fn is less than or equal to c dot gn for all n greater than or equal to n naught, where c is equals to 2 and n naught is equal to 3. You can take n naught equal to 3 or n naught equal to 4, doesn't matter. But here I'm taking the lesser value. So for these two constants, we can say that fn is less than or equal to c dot gn, right? So we can clearly say that fn is equals to big O of n square. This is the quadratic growth, right? That is why we are getting n square over here. And obviously you can see the dominating term is n square in this case, and the rest of the terms after some time will get negligible. So it is clear that fn is equals to big O of n square. So the time complexity, that is the worst case time complexity, is big O of n square. So in this way we calculate the time complexity for different scenarios, like when we have consecutive statements, when we have loops, when we have nested loops. We will also see some more guidelines, but we will see them in the next lecture. Okay friends, this is it for now. Thank you for Let's continue our discussion on guidelines for asymptotic analysis. We will discuss about the if-then-else statements. How much time a particular program will take when we have if-then-else statements. Let's say we have this program which consists of if-then-else construct, and we are asking here the input from the user, and then we will check this condition. Is n equals to 0? If that's the case, then we will evaluate this statement, else we will go in within this else construct and will evaluate this statement n number of times, right? The worst case running time in the case of if then else construct is evaluate the running time of the test part, that is this part, then add it with the running times of the if part or else part, whichever is larger, not both the parts, let me tell you. Because at a time we are either executing the if part or else part. Whichever is taking the larger time, we will add this to the test part. This is how we will calculate the running time of the if then else construct. This is as simple as that. For if part, obviously this condition checking will take just constant amount of time, and the statement within this if construct will also take constant time. That's my assumption, of course. You should assume that the statement, when I'm writing this in the comment section, then it will always take constant time. That is the assumption, okay? Then the total time in this case will be 1 plus 1, which is equals to big O of 1. Doesn't matter, this is 1 plus 1, which is again a constant, right? So the worst case time complexity will be constant. That is big O of 1. So it is a constant growth. This if construct will take constant amount of time. Now let's evaluate the else part. Here in this case, in the else part also, we need to evaluate the running time of this particular statement. That is this condition checking, right? N equals to 0. This will take constant time, right? Because it doesn't matter whether we will evaluate the if part or else part, we always have to check this condition. In order to get into the else part, you have to check this condition. So this must be calculated in the case of else part as well. So the running time for this statement must be calculated in the case of else part as well. Apart from this, you can see that within this else part, we have this for loop which runs from I equal to 1 to n. And within this for loop, we have the statement. So this statement will get evaluated n times. So it is clear that this statement is executed n times. So the total time will be 1 plus n, which is equals to big O of n, right? So what is the overall time complexity? It is big O of n, because this else part is taking the larger amount of time. Test part plus the else part will give us this time complexity, that is big O of n. Now the next guideline, that is about logarithmic complexity. What is logarithm, by the way? Let's take this example and try to understand what is the meaning of logarithm. What does this statement says? The above logarithm says that how many times 2 has been multiplied by itself. I'm talking about this 2. How many times 2 has been multiplied by itself in order to obtain value 8. 2 has been multiplied 3 times, right? 2 into 2 into 2 is 8. So 2 has been multiplied 3 times. That is why log 8 base 2 is 3. So this is the meaning of logarithm. It always gives how many times a particular base has been multiplied by itself in order to obtain the value under consideration. So answer is 3. Logarithmic time complexity is achieved when the problem size is cut down by a fraction. Let me tell you that logarithmic time complexity is lesser than the linear time complexity. It is achieved when the problem size under consideration is cut down by a fraction. How is that so? Let's see the example over here. Here you can see this for loop runs from 1 to n, and we are evaluating this statement. You think of this that this for loop will run n time, but here's the catch. Here I is not incremented by 1, but I is multiplied by 2 every time. So here in this case, obviously this is not a normal growth, right? This is not the case that this will run from I equals to 1 to n, total n times. No, it is not the case. Here I is not incremented by 1. It is not a step size increment. I is multiplied by 2 every time. How to evaluate the time complexity in this case? In the iteration number 1, initially I is equal to 1, right? So initially I is equal to 1. So this is equal to 2 to the power 0. Can we say that 1 is equal to 2 to the power 0? This gives 1. I'm writing this in this form, okay? In the iteration number 2, I will be 2. We can write this 2 in the form 2 to the power 1. Isn't that so? Now in the iteration number 3, I will be 4, not 3, right? Because I is multiplied by 2. Here previously the value of I is 2. 2 is multiplied by 2, which gives 4. We can write this as 2 to the power 2. Similarly for iteration number 4 and iteration number 5, here in this case we are getting I equals to 8 and I equals to 16. We can write this in this form 2 to the power 3, 2 to the power 4. Let's say we go up to iteration number k. Then in that case this will be 2 to the power k minus 1, because you can see over here that for iteration number 1 this is 2 to the power 0. Iteration number 2 this is 2 to the power 1. It is always 1 less than the iteration. So here in this case, if we are going up to iteration number k, then this will be 2 to the power k minus 1. And this is equal to n, because the last value over here is n. When I is equal to n, this is what we are getting. This is 2 to the power k minus 1. This is the last iteration. So we know that n is equals to 2 to the power k minus 1 at the end. Now we need to calculate how many iterations are there. How many times the statement under for loop has been evaluated. For this purpose, we will apply log on both sides. When we apply log on both sides, this will be log n base 2. This will be log 2 to the power k minus 1 base 2. This gives k minus 1 only, and this will be log n base 2. So k minus 1 is equals to log n base 2, which gives k equal to log n base 2 plus 1. So the time complexity is obviously big O of log n base 2. Obviously we are eliminating this constant term, it doesn't matter. So here the time complexity will be log n base 2. Isn't that so? Let's consider one example to understand this properly. Initially I is equals to 1 and this loop runs up to 32. But let me tell you that we are incrementing not by step size. We are multiplying I by 2 every time. So again, we know that how many iterations this particular for loop will run for. We need to calculate the number of iterations so that we could get that how many times this hello will get printed on the screen. Or we can calculate the time complexity, that how many times this statement has been evaluated. So this is given by k, and we know that k is equals to log n base 2 plus 1. Here we know that n is equals to 32, right? So let's replace this n by 32 over here. This gives log 32 base 2 plus 1. Log 32 base 2 is 5 and 5 plus 1 is 6. So number of iterations are 6 in total. So this means that hello is printed on the screen 6 times. So the time complexity is obviously log n base 2, right? Let's consider one more example here. Here in this case, we have reversed everything. Instead of I is equals to I into 2, we have I is equals to I divided by 2. Let me tell you that this will also take logarithm time. We are running this from I equals to n up to 1, just reversing the whole sequence. The time complexity will again be logarithm, okay? Let's see how. In the iteration number 1, I is equals to n divided by 2 to the power 0. In the iteration number 2, I will be n divided by 2 to the power 1. Why this is I equals to n divided by 2 to the power 0? Because we know that initially I is equals to n. We can write this in this form. Then I becomes n by 2, which means I is equals to n divided by 2 to the power 1. Then it will be n divided by 2 to the power 2. And so on. This will go up to n divided by 2 to the power k minus 1 for iteration number k. And this is equals to 1 because lastly we are getting this 1 value, right? This is not equal to n. This is equal to 1. So n divided by 2 to the power k minus 1, which is the last iteration. So it is equal to 1. N divided by 2 to the power k minus 1 is equal to 1, which means that 2 to the power k minus 1 is equal to n. This is similar to the previous case, isn't that so? Again, we will apply log on both sides. This will give us k minus 1 equals to log n base 2. And finally, k is equal to log n base 2 plus 1, which is again big O of log n base 2. We haven't done anything. We have just reversed the whole sequence. Again, we are getting this logarithm time complexity. So this is all about the guidelines related to asymptotic analysis. And now you are aware about how to calculate the time complexity in different
Okay, so a while ago, no, the first video presentation, no, this show you an example of a looping, no. Again, looping is a common operations in data structures, no. Particularly, no, when iterating over the elements in data structure. So to perform some operations on each element, there are certain functions or different types of looping in data structures. Last time we discussed it already, the arrays, no? Because to loop over the elements in an array, we can use a for loop with the index variable running from 0 to n minus 1 or n plus 1, where n is the size of the array, for example. Then another, of course, for linked list. No? Our video presentation also shows that to loop over the elements in the linked list, we can use a while loop to traverse the list starting from the head node and moving the next node until we reach the end of the list. Okay? Then another example earlier is the trees. Now, to loop over the elements in a tree, we can use a recursive functions that visit its node in the tree in a specific order, either pre-order yan, in order yan, or post-order. Okay, so to continue, okay, looping is a fundamental operations in data structure that allows us to perform operations on each element in the structure. So different data structures require different looping strategies, but the basic concept is the same. Now, iterate over the elements and perform some operation of each element. Okay. Okay. So, wait. Okay. So I just want to turn on my camera, no. Again, as what I mentioned earlier, no. In addition, no, for the looping, there are many other types of data structure where looping is a common operations. We were done already a while ago. No, I mentioned about arrays, linked lists, trees, and of course, additional is the stacks and keys, no, or queues, no. To loop over the elements in a stack or a key, we can use a while loop to pop or the key each element until the stack or key is empty. Okay, so we use a command for it, like let's say for example stack.push, no. We use of course the stack that is empty command, and so on. Then another is the hash tables. To look over the elements in a hash table, we can use a for each loop to iterate over the key value pairs in the table. Okay? Then another is the graphs. No? To look over the vertices and edges in the graph, we can use a recursive function or an iterative algorithm that visits its vertex and edge in the graph in a specific order. Nandiyan po yung depth per search, breadth per search, wherein we could able to use, let's say, this command, no, that command, graph, and so on. No? So these additional examples demonstrate how data structures may require different looping strategies depending on their implementation and the nature of the data they contain. However, the basic concepts of looping remains the same. Iterate over the elements and perform some operations on the element. Though, there are some guidelines for performing asymptotic analysis. No? Number one, we need to focus on the dominant term. No? In asymptotic analysis, no, we are interested in the behavior of the functions as the input size approaches infinity. As a result, we can ignore lower order terms and focus on the term that dominates the growth of the functions. So, some guidelines also cover the use big O notation, because as what we discussed last time, big O notation is a mathematical notation that describes the upper bound of a function's growth rate. It is commonly used in asymptotic analysis to describe the time or space complexity of an algorithm. So, when using big O notation, we only consider the highest order term in the functions. We need also to consider the worst case scenario. No? When analyzing the performance of an algorithm, we typically focus on the worst case scenario, which is the input that results in the highest possible running time or space usage. This ensures that we have an upper bound on the algorithm's performance regardless of the input. Don't ignore constant. While asymptotic analysis is focused on the growth rate of a function, it's important to remember the constant do matter, because an algorithm with a smaller big O notation may be slower than an algorithm with a larger big O notation if the constant factor is larger. And we need to be careful with recursive algorithm, because a recursive algorithm can be tricky to analyze using asymptotic analysis, as the running time can depend on the number of recursive calls. In this case, it's important to come up with the recurrence relations that describe the running time of the algorithm and solve it using mathematical technique. So, asymptotic analysis, again, is a powerful tool for analyzing the performance of an algorithm. So by focusing on the growth rate of the function and using big O notation, we can compare the efficiency of different algorithms and determine their scalability as the input size increases. Okay, I just want to give you an additional video presentation, no, focusing on sample asymptotic analysis solving problem. Okay, so this will be a 3-video presentation, a continuous 3-video presentation, wherein, as I mentioned, this will be an asymptotic solving problems. No? Wait.
Here in this presentation, we will consider solve problem 1 related to asymptotic analysis. So let's get started. What is the time complexity of the following program? The program is available in front of you. You need to determine the time complexity of this particular program. Here you can see this is not a complete program. Only a function is given in front of you. And let me tell you that this function accepts one argument, that is value for n. And within this function, we have these statements written over here. So you can clearly see that the first statement is I am declaring 3 variables and one more variable, and I have initialized this variable with value 0. This is a count variable which has been initialized with 0 value. Then we have these for loops which are basically nested for loops, and within this for loop we have the statement count plus plus. You need to determine the time complexity of this program. It would be better if you can pause the video for a while and try to answer this question on your own. I hope you're done. Okay, let's move on to the solution. Now let's take this statement first. Here you can see I have declared 3 variables and one more variable count, which has been initialized to 0. These 3 variables haven't been initialized. We will use these 3 variables within this for loops. You can see the time complexity in this case is big O of 1 because it's just taking a constant amount of time for the execution. There are no for loops, nothing special. You can treat this as a single statement. Although you can write these in multiple lines as well, but treat this as a single statement. If you treat them with different statements as well, then also it will take constant amount of time. Isn't that so? So this particular statement is just taking a constant amount of time. Now let's consider this particular statement. This is nothing but a for loop, right? Within this for loop, we have another for loop. And within this for loop, we have another for loop. Then we have this statement. Obviously, our task is to find how many times this particular statement has been executed. So let's first evaluate and try to understand what this for loop is and how much time it will take. In the iteration number 1, you can clearly see that I is equals to n by 2, right? You can write this as I equals to n by 2 plus 0. Now in the iteration number 2, it is clear that this will be I equals to n divided by 2 plus 1. Because you can clearly see over here that this is I plus plus, an increment by one step. So obviously in the next iteration, this will be n by 2 plus 1. In the iteration number 3, this will be n by 2 plus 2. In the iteration number 4, this will be n by 2 plus 3 and so on. Now let us assume that we are running up to iteration number k. In that case, I will be equal to n by 2 plus k minus. Here you can clearly see in the iteration number 1, this value is 0. Iteration number 2, this value is 1. While this n by 2 remains constant, only this value is changing with the iterations, right? In the iteration number 3, this will be 2. Iteration number 4, this is 3. So similarly, in the iteration number k as well, this will be k minus 1. So I will be n by 2 plus k minus 1, which is equal to n, because this is the last iteration we are considering. But we don't know how many times this has been executed. That's why I have taken this as k. So at this particular iteration, I is equals to n by 2 plus k minus 1, which is equal to n. Now let me rewrite this over here in a proper manner. This is n by 2 plus k minus 1 equal to n. Let's solve this. We can write this k minus 1 equals to n minus n by 2 without any problem. I can bring this n by 2 over here. By solving this, this becomes k minus 1 equal to 2n minus n divided by 2. Again, we can write this as k equals to n by 2 plus 1. This means that our loop is running n by 2 times. I can take the least upper bound as n without any problem. Loop executes n by 2 plus 1, which can be thought of as n by 2 times only, because plus 1, if we won't consider, then it will not cause any problem. We can take the least upper bound as n without any problem. So this loop is actually running n times. Although it is running n by 2 times, let me tell you, but we are taking the least upper bound without considering the constants. So least upper bound of n by 2 is obviously n. So we can say that this loop is running n times. So this is big O of n. Now let's consider the next loop. Here in this case, you have j equals to 1, and this is quite interesting. Here it is written j plus n divided by 2 less than or equal to n. And here it is just j plus plus. Let's see what is happening over here. In the iteration number 1, it is clear that j is equal to 1, right? In the iteration number 2, j is equals to 2. Iteration number 3, j is equals to 3. Iteration number 4, j is 4, and so on. At iteration number k, j will be equal to k without any problem, because here in iteration number 4, we have j equals to 4. Iteration number 3, we have j equals to 3. So it is clear that in iteration number k, j is equal to k, which is equal to n by 2. Why I am writing this as n by 2? J plus n by 2 less than or equal to n can be written as j less than or equal to n minus n by 2. I can bring this n by 2 over here. This becomes n minus n by 2. I can solve this and this brings me n by 2. So j is eventually less than or equal to n by 2. I can say that k is equal to n by 2 without any problem. So it is clear from this fact that this loop is running n by 2 times. I can take the upper bound as n and can clearly say that loop is running with the time complexity big O of n. So this is the upper bound I can take, which is n instead of n by 2. Always try to remove the constants. Don't take n by 2. Instead of n by 2, you can take a least upper bound. That could be n. Now let's see the other loop. Here in this case, obviously, we can clearly understand that k is equal to 1 and k is less than or equal to n and k is equal to k into 2. we have already calculated the time complexity when these loops are available. Here in the iteration number 1, k is equal to 1. 1 can be written as 2 to the power 0, 2 can be written as 2 to the power 1. Similarly, 8 can be written as 2 to the power 3, and so on. If I consider this up to iteration number p, then this will be 2 to the power p minus 1, which is eventually equal to n. Because in the last iteration, 2 to the power p minus 1 is equal to n. You can clearly see over here. I can say that 2 to the power p minus 1 is equal to n, or n is equal to 2 to the power p minus 1 without any problem. I can take log on both sides. This will become p minus 1 equal to log n base 2. I can write this as p equals to log n base 2 plus 1, which is equals to big O of log n. I can eliminate this constant. So I can say that the time complexity for this loop is big O of log n. Now let me tell you, these are nested for loops, right? So obviously you know that we need to multiply these three time complexities. N into log n, which is equals to big O of n square log n. So I can say that the time complexity for this particular code is big O of n square log n, or order of n square log n. So this is the time complexity of this particular code. This loop is running n times. I have taken the upper bound. This loop is also running n times. Again, I have taken the upper bound. Here in this case, this loop runs log n times. This is nested for loop structure. So here in this case, we need to multiply these three time complexities. N into log n will give us n square log n, which is the final time complexity. This statement is executing n square log n times. So this is the time complexity of this particular code. Now here is one homework problem for you. The program is available in front of you. Again, we have three nested for loops. You need to determine the time complexity of this program. And obviously, you can post your answers in the comments. Let's consider solve problem 2 on asymptotic analysis. What is the time complexity of the following program? Here is the program available in front of you. You need to determine the time complexity of this particular program. It would be better if you can pause the video for a while and try to answer this question on your own. I hope you're done. Okay, let's move on to the solution. Here you can see this statement is going to take only a constant amount of time, while this statement is also going to take a constant amount of time. Think of this as these two statements are going to take constant amount of time. Here you have the if construct, which says that if n is less than or equal to 1, then return. That's it. There's nothing else in this code. Here in this case, you are declaring two variables, I and j. Both of these statements are going to take constant amount of time. Okay? So mark the time complexity in this case as constants, right? Now coming to the for loop here. Here this for loop executes n times without any problem. You can clearly understand that this loop is running from I equals to 1 to n. And here the increment is by one step. Therefore, it is clear from this fact that this loop is executing n times. I think there is no problem in understanding this, right? Now let's come to the inner loop. This is very important, let me tell you. Here also, this loop is running from 1 to n, and there is obviously an increment of one step. Now my question is, how many times the inner loop will get executed? If you think it will be executed n times, then you need to think again. I want you to think about this because this is very important. Here if you think that this loop will execute n times, then you need to think again, because there are some other statements you need to figure out in this case. Here you can see within this for loop we have a printf function. Obviously it prints hello on the screen, and after that we have a break statement. Now this is interesting. I want you to focus on this break statement. What does it mean? We have a for loop which runs from 1 to n. But let me tell you, when the condition is satisfied for the first time itself, the printf function will get evaluated, and after that the break will also get evaluated. When the break is evaluated, obviously we come outside of this loop. Isn't that so? So for the first iteration itself, we are getting out of the loop. It doesn't matter whatever the value of I would be. This loop will run only one time. Isn't that so? Here you can see when I is equal to 1, we get inside this loop. When j is equals to 1, we get again inside this loop. Here we will print hello on the screen, and after that break statement get evaluated. Because of this break statement, we get outside of this loop immediately. No more runs. So what we were thinking about, that this loop will run n times? No, it is not the case. Because of this break statement, we immediately get out of this loop. No matter what is the value of I, inner loop runs only one time. I think this idea is quite clear, right? We can rewrite these two for loops in a single for loop, isn't that so? Here you can clearly see that no matter what, this loop will run only one time. Why can't you simply eliminate it? There is no need for this for loop, right? This loop runs from 1 to n, that's what our thinking. But because of this break statement, this loop is running only one time. So it is clear from this fact that if we eliminate this for loop, then also there will be no problem. You just keep the outer loop. You can rewrite this as for I equals to 1, I less than or equal to n, I plus plus, printf hello. So it is clear that the time complexity is big O of n, right? Time complexity is big O of n. It is not n square. Now here comes the homework problem for you. What is the time complexity of the following program? Program is available in front of you. You need to determine the time complexity. After getting the answers, you can post your answers in the comment section below. Okay friends, this is it for now. Thank you for watching this presentation. Let's consider solve problem 3 on asymptotic analysis. And here's your problem. What is the time complexity of the following program? The program is available in front of you. You need to determine the time complexity. It is better if you can pause the video for a while and try to answer this question on your own. I hope you're done. Okay, let's move on to the solution. Here you can see again, this statement is going to take a constant amount of time. There's no loop, there's no multiple executions, just a single statement. Here you can see I have declared variable I and variable j. This declaration is going to take a constant amount of time. After that, we have a for loop, which is an interesting for loop, right? We have this I equal to 1. We are running this up to n by 3. And obviously the increment is by one step. So you can clearly say that in the iteration number 1, I is equal to 1. In the iteration number 2, I will be 2 because we are incrementing by one step. Therefore, in the iteration number 2, I will become 2. In the iteration number 3, I will become 3. In the iteration number 4, I will be 4. And so on. If you run this up to iteration number k, then I can say that I is equal to n by 3, which is equal to k. Because in the last iteration, I is equal to n by 3. We are assuming that we are running up to k iterations. That's why I is equal to n by 3 is equal to k. As k is equals to n by 3, as we are running this loop n by 3 times, I can take the upper bound on it, which is n. So big O of n is the time complexity. But let me tell you that I have taken the upper bound on it, right? Why I'm not taking n by 3? I'm taking the upper bound. I'm just eliminating the constants and simplifying this and writing this over here n. So it is clear that this loop runs n times, right? Now let's consider the another for loop. Here this loop is running from 1 to n, but you can see over here the increment is by 4 steps, not by a single step, right? So let's consider the iterations. In the iteration number 1, j is equal to 1. In the iteration number 2, j will be 1 plus 4 because the increment is by 4 steps, right? So you need to add 4 to this. This is 1 plus 4. In the iteration number 3, this will be 1 plus 4 plus 4, which is equal to 1 plus 2 into 4. I can write this 1 plus 4 plus 4 as 1 plus 2 into 4. There is a reason behind this, why I'm writing, I will tell you later. In the iteration number 4, this will be 1 plus 3 into 4. Similarly, in the iteration number k, this will be 1 plus k minus 1 into 4. Now you can clearly see why I have written 2 into 4 over here and 3 into 4 over here, right? Because in the iteration number 3, this is 2. In the iteration number 4, this is 3. Similarly, in the iteration number 2, this is 1. And iteration number 1, there is nothing over here. So it is clear that in the iteration number k, this will be 1 plus k minus 1 into 4. And this is equal to n, right? Because in the last iteration, we have n over here. So 1 plus k minus 1 into 4 is equal to n. Let's solve this. I can bring this 1 over here. This becomes n minus 1. After that, I can bring this 4 in the denominator and this becomes n minus 1 divided by 4. Again, I will bring this 1 over here. This becomes n minus 1 divided by 4 plus 1, which is equal to k, right? So basically, this loop is running n minus 1 divided by 4 plus 1 times. I can take the upper bound on it, which is big O of n. Now you can clearly see how many times this printf function has been evaluated. We have evaluated these two for loops. This for loop is running n times. This for loop is also running n times. So the total time complexity in this case is big O of n square. Isn't that so? Again, we are choosing the upper bounds. This is very important. You should take the upper bounds, not the exact times. Here obviously this loop is running n by 3 times, but we have taken the upper bound, right? The upper bound is n. So what we are assuming that this loop is running n times. And we are also assuming that this loop is running n times. Because this is a nested for loop structure, the total time will be big O of n square. So this is the time complexity of this particular code. Okay friends, this is it for now. Thank you for watching this presentation.
Okay, so uh, again, based on the given video's presentation, no, it shows some different programs, no, demonstrating the application of asymptotic analysis, no, because asymptotic analysis is a powerful tool for solving problems in IT and other fields. So by analyzing the growth rate of a function, we can determine how the algorithm's performance scales with input size and make informed decisions about the most efficient way to solve a problem. So, let's say for example, no, suppose we are given an unsorted list of an n integers and we want to find the maximum value in the list, no? One way to solve this problem is to simply scan through the list and keep track of the maximum value seen so far. So, this algorithm has a time complexity of O multiplied by N, meaning that the running time grows linearly with the input size. Alternatively, we could sort the list using the sorting algorithm like quick sort or merge sort, which have time complexity of N of O multiplied by N log N, no, in the average case. So once the list is sorted, we can simply return the last element as the maximum value. So while this approach has a higher asymptotic complexity, it may be faster in practice for a large input size due to the constant factors involved in the sorting algorithm. Another example where asymptotic analysis is useful is in analyzing the performance of the data structure. For instance, suppose we need to store a large number of elements and perform frequent insertions and deletions. We could use an array which has a constant time complexity for assessing elements, but has a linear time complexity for insertion and deletions in the worst case. Alternatively, we could use a balanced binary search tree like a red-black tree, which has logarithmic time complexity for all operations in the worst case. So in summary of our topic for today, asymptotic analysis is a powerful tool for solving problems. No? By analyzing the growth rate, we can determine how an algorithm's performance scales with input size and make informed decision about most efficient way to solve a problem. Okay, so I think that's it for today because we already finished the discussion of asymptotic algorithm or analysis. No, it's very technical actually. No, but I will show you a lot of examples, a demonstration of programs, a simulation of a program at the same time for you to understand this asymptotic analysis.